All right, so we talked a lot about calculator approaches last time, and that's all well and good. The calculator gets you a nice streamlined approach to be able to come up with graphs and things like that. But also, I mean, at some point you got to put it down on paper. So these equations aren't too crazy. So I figured we just do it by hand, and we'll go to the calculator when it really is needed. I gotta get this out of my face. It's killing me. All right, so just plugging and chugging away. The x values, the y values. Now, the y values are the easier ones to manipulate because we're just doubling whatever the t value is. All right, so that's kind of nice. So there's not really any thinking involved in that. So we're looking at -4, -2, 0, 2, 4, and 6. Now, for the x values, we're squaring each one and subtracting the 4. So square the -2, you get a 4 minus 4 is 0. And so the first entry, the first ordered pair that you're going to plot is 0, -4. All right? The t just tells you what time it'll be at that position. All right? So plug in a -1, square -1, you get a +1 minus 4 is -3. -4, -3, 0, and then we're looking at 5. All right? So each one of these columns that we just produced comes together with the other one to make ordered pairs that we can then plot. All right? So that's what we're looking at. And I'll show you the role that the time plays in the construction of the graph. So 0, -4. Plot that. It's about right here. -3, -2. -4, 0. -3, +2. Trying to make it a nice filled-in circle. 0, 4. And finally 5, 6. So I got to scroll over a little bit. All right, connect it with a nice smooth curve. I'm going to change my thickness. Just got to remember to change it back. All right, now this is a portion of a sideways parabola, which, yeah, I don't know that you're going to necessarily pull sideways parabola from the equations, but you could see that one of the equations has a power of 2 in it, so it's got a parabolic aspect to it. So we're not stunned that this ended up being a parabola. It's just the orientation of it might be interesting. You know, we also want to indicate the flow of the curve, all right? Because it started at 0, -4, and it worked its way around in a clockwise direction. So using arrows, I'm just going to indicate the direction of the flow. Some people put their arrows right on the curve. That's fine too. All right. All right, example 2. We're looking at a projectile. Again, something looking very much parabolic. All right, just because it's the same structure as number 1, except it's the other way around, where the linear part is x and the parabolic part, or the quadratic part, is y. So if an x equation being quadratic gave us a sideways parabola, then it's possible that the case where the quadratic is part of the y equation would make a vertical oriented parabola. Sure.
Since how do you show the time on this? Because time never starts at negative, it always starts at positive. How do you show negative?
Well, how do you relate to it?
How do you, like, if you want to describe it, I can't do that.
Yeah, so time can be both positive or negative. It depends on the situation. So you have, and it could be equal to 0. My classic analogy is the case of a person running around a track. So if that person starts when you start the clock, then negative time has no meaning, right? Because there's nothing being measured prior to them running. Now, if they've been running for a little while, and then you show up and then start keeping time on them, then negative time would have meaning because it just represents the amount of time that was elapsing prior to you getting there. All right, so negative 5 seconds would be just before you started the clock. All right, another one, I don't think it's in this course, but I did an example, I think it's Calc 2, did an example where an elevator starts on a high floor and it's going in a downward direction, and you're on like the 23rd floor or something like that. And so that's another situation where negative time could have meaning, because if it's going in a downward direction, you're 0. Anything prior to it reaching your floor would be negative time. Yeah. So this one we expected to be a vertically oriented parabola because of the equations, yeah, but also because it's a projectile, and the path of a projectile is parabolic in nature, but of the vertically oriented variety. All right, so the x values, we just get those by taking our t values and multiplying by 20. All right, so 0, 10, 20, 30, 40, 50, and 60. That's kind of nice. Then we're subtracting 16 times t squared from 64. All right, so if I'm starting at 0, or t equals 0, I'm not subtracting anything from the 64. All right, for the second one, 1/2 squared is a quarter. A quarter of 16 is 4. All right, so 64 minus 4 is 60. Now, if it were linear, we'd be able to follow the trend, but it's not the case. Subtracting 16, we're looking at 48. All right, the next one is 3/2 squared is 9/4. 9/4 times 16 is 36. 28. All right, so we're subtracting 28, so 44. Or are you telling me the result?
The result.
The result, okay, so yeah, we are subtracting 36. So the result is 28. All right, I thought I did the mental math wrong, which I guess could happen. This one's 0, right?
Yep.
After that, it's debatable whether you actually even care, because the y value represents the height, right? We're assuming that the ground is something that is like not really permeable. So when it hits the ground, it's on ground level. It's not going to burrow its way through the ground. But yeah, it gave us a table of values, so let's plug them in. All right, the next one, plugging in 5/2, so it's 25/4. So we're subtracting 100, negative 36.
Yep.
All right. So 36 somethings below the ground. Feet, inches, miles, 36 miles, a little intense. 144, so negative 8?
Yes.
Yeah, all right. Starting to get good at math. Nice. Good moment for me. All right, so let's see how many boxes there. 1, 2, 3, 4, 5, 6, 7, 8. Well, almost 8. We'll pretend it's an 8 box. It's a little smaller in size, but we can live with it. 1, 2, 3, 4, 5, 6. Actually, we're not going to have enough on the low side, so we might as well maybe go by 20s. Not on the y-axis. On the x-axis, we could go by 10s. If you just indicate what the scale is, you don't have to label them. I'm just doing it because I don't want to think when I'm actually plotting. 40. Alright, so 64, right about here. 60. 48, like right about here. Oh, that should be at third. Oh, because it's not at zero. What am I doing here? What's going on here? Zero. Did I missed one definitely. Oh wait, no, I haven't missed it yet. I was about to miss it. I was about to skip over the 3028, but I think I'm good. Shockingly. 50, negative 36. We're talking about like right here. And then 60, negative 80 is right about here. All right. So let me increase the thickness. I can't see the points, but I went for it anyway. Okay, so we just have to indicate the flow, downward direction, and then we're good. Now, so the shape of the trajectory, that's easy enough, it's parabolic. Might look more parabolic on your papers than on mine. I mean, this is the best I can do. When does the projectile hit the ground? Right? So that would be, if you're just looking at the graph, you're looking at specifically this location here. Right? So hits the ground. Yep. After 2 seconds. All right, because it said when. All right. Could have asked something like how far away was it when it hit the ground, but that's more of a pre-calc question. Actually, I mean, who am I kidding? This is all pre-calc anyway. All right. I mentioned that last time that like these are the topics that may or may not have happened in your pre-calc class, so we're doing it anyway. If you've seen this before, you're like, oh my God, this is brutal. That's good. All right, we'll ease you into this semester. If you haven't seen it before, you're happy that I'm going over it like this, because when we actually apply the calculus to this, it would make 0 sense without having the pre-calc component explained. All right, and you know what? All right, so you have XY equations, and then you have not XY equations. Well, kind of. I mean, X in terms of T, Y in terms of T. So when an equation, a single equation describes the path of an object, you know, maybe projectile motion or something like that, and it's strictly in terms of X and Y, that's known as a rectangular equation, right? Also known as a Cartesian equation, but if I were to say it like that, it's like I'm trying to impress you and I'm not, or at least not in that area. So, rectangular. The reason why it's called rectangular is because the graph grid is rectangular. You might say square, but I would say not necessarily, because if I scale my axes, then the x dimension and the y dimension aren't perfectly in lockstep. Like if I'm going by 2s here and 5s there, you have different sizes of your rectangles, even if they still appear to be square. All right? When you get into polar coordinates, they're not rectangular because the graph that you're using to plot points is a polar graph. It's not a rectangular graph, all right? So when you think of the term, think of what you would be graphing it on, what kind of graph paper, and that usually gets you where you need to go, all right? So converting to rectangular form, it's really just substitution, all right? So I'd be looking at this set of equations. There's a few ways you could tackle this one, but right off the bat, I see that I have this equality. 2t and x are the same thing. All right, well, here's a 2t. I could replace that with an x. Rectangular. Y equals 4 minus x. I always found that it was easier to learn through problem solving than it was to learn through reading steps and somebody else's definitions and things like that. Now, this is not a proof, but I would now have it in my mind that if my x and y equations each had a linear form, then what you would be dealing with is the graph of the line. On the previous page, we learned that if one part of your parametric equation set is linear and the other part is parabolic, you're dealing with a parabola. It's just a question of which way, up, down, or left and right, right? So we're able to generalize. I mean, and then there's some obvious things, like if you see a sine function in there, like x equals the sine of t, yeah, it's going to be a trig graph. I mean, but not because you drew some advanced conclusion, but because it's got a sin in there, you know, like it has to be, all right? Sometimes they're not as cut and dry, so you got to do a little bit of background work. And so, in the case of number 4, I would solve my second equation for t. T equals 2y. Now, I'm only choosing the second equation because it's the easier of the two. All right, so now I have a relationship between t and y. I can now replace the t with what it's equal to, and that's the 2y. X equals 2y squared minus 4. And then I can clean it up. 4y squared minus 4 equals x. This is my rectangular form. Now, another thing, so I'm throwing a lot of like side commentary at you tonight, but that's because it's the beginning of the course and you're still feeling me out and I'm still trying to get across the way I do things. It said convert into rectangular form. It didn't say anything beyond that. It didn't say simplify, it didn't say put your answer in standard form. It didn't say anything like that. It said convert into XY, well, essentially XY form. It said convert into rectangular form, which means the second you get rid of t and you're left only with x's and y's, you're done. All right? The only time you got to go further is if I ask you to simplify, which usually happens once, maybe twice per test. Every other time, it's take the derivative, convert. If I say simplify, then you go the distance. If I don't say simplify, what that means is if you do simplify, then it's at your own risk. All right? Because some people, I mean, you can't just leave an answer as something like 2y squared minus 4. You're like, you know what? I just got to clean it up. I'm not going to leave it like that. Or maybe it's just ingrained in you. Like back in the day, you know, middle school, teacher giving you a hard time because you didn't simplify even though the directions didn't tell you to. Yeah, that could be the case. But if you do it and screw it up, you're going to lose credit. All right? So if I don't tell you to simplify, but then you take it upon yourself to simplify and then mess it up, anything that you put down on paper is up for evaluation. So I look at it and say, okay, you wanted me to grade this. Well, it's incorrect. All right? So I personally would not take the chance, but that's me. All right? Now, number 5, the phrasing of number 5 is a work in progress, right? Because I just said simply find the derivative of your answer to example 4. I didn't say in any particular way. Derivative of x with respect to y, derivative of y with respect to x. So it's really up to you to do it any way you want. All right. So you have an equation here that's solved for x in terms of y. So I've struggled with the phrasing of it only because there are some folks that they get it in a rectangular form, x equals, and then they say, well, I don't want it as x equals, I want it as y equals. So then they add the 4, divide by 4, take the square root, and get this radical with a plus or minus of the mess. Okay? There's nothing wrong with an equation being solved for x in terms of y. All right? Hopefully that's not new information for you. Hopefully you kind of experienced that in Calc 1 and Calc 2. But there was a point in time in algebra courses where having an equation solved for x in terms of y was not what you were expected to be doing. All right. So if you had it in that form, you had to solve for y. All right. Now it's, hey, what way is cleaner? Solving it for x in terms of y or solving it for y in terms of x? In this case, x in terms of y. Okay. So I'm going to take the derivative of it just the way it is. But normally I would say dy dx, but it's backwards. X and y are swapped. So this is dx dy. All right. Now, if you wanted to, you could do it implicitly, but I think that's making more work for yourself. All right. So this is going to be 8y because we're doing it in terms of y. All right. Yeah, I mean, it's a couple extra steps if you do it implicitly. Now, you could, if you want, or write it as dy dx, change y in terms of x, and take the reciprocal 1 over 8y. It's another way. I mean, it's just an extension of that. It's like you look at the dx dy and you say, I don't want that. It's supposed to be dy dx, just like my teacher told me. So flip it, if that makes you feel better. All right. If you want to do it implicitly, I could just run through that real quick. All right. So if I do it implicitly, I started off originally with x equals 4y squared minus 4. Oh, it was right there in front of me. I didn't even have to scroll. Taking the derivative of y with respect to x, that for the implicit approach, left-hand side just becomes a 1. Right-hand side, 8y times dy dx. Because the derivative of a constant is 0, so that's going to go away. And then when I solve for dy dx, I end up with this. So, you know, a couple extra steps, maybe one extra step, 1.5 extra steps, depending on how you look at it. All right. So, and we'll get to the trig one in a second. What you could do is go back, if we wanted to put it in parametric form, we know y is equal to t over 2. Yeah. So I can take my dx dy and replace the y with t over 2. In which case I would get 4t. All right, so this open-ended question, which didn't seem so open-ended when you first looked at it, take the derivative, okay, I'll just use power rule and stuff. It opened up this pathway to things. Now, hopefully, a thought that's going through your mind is something along the lines of, is there a way that I can get to these derivatives without doing the conversion? Because these problems that we're converting, they're not the challenging problems. Some of them can be a little crazy, right? Is there a way that we could find the derivative of a parametric equation, parametric set of equations, without having to convert it into a rectangular form first? And I would even follow that up by saying, if there was not a way to do that, then I would question why we're learning parametric equations to begin with, right? You know, it's like, what's the point of this if I can't do the calculus to those parametric equations, all right? But before we get there, let's tackle a trig problem. All right, for the trig ones, we want to rely on known facts. Sure.
You solve it in terms of x. What if you had to do it in terms of y? Just like we normally do.
Yeah.
dy dx, substitute it for x and y. D for x and y.
Yeah,
It was the same. I didn't know that.
You would get an equivalent answer. It's just your solution. I could just do it off on the side here. What you'd be looking at is this, solve for y. So I'd add the 4, divide by 4. So we're looking at y.
I'm talking about the substitution on the top. Instead of using
Oh.
e as x on the top, substitute for...
Go the other way. So
Yeah, the other way.
yeah, you'll get something equivalent.
No.
I guess it doesn't matter. So here, I would add the 4 and then take the square root.
Square root.
Just don't forget the plus or minus.
Okay.
All right? Because if you forget the plus or minus, then it's not equivalent.
Then you get 2 derivatives you have to do.
Right.
One for plus.
Yeah, exactly.
How's it so different? Like you did the same parametric equations, and you get 3 different answers.
Yeah, 3 different answers, each meaning something different. Yeah.
How would we know whether you're right on the right track or the wrong track? How do you know?
Well, this question is purposely open-ended,
Okay.
so I would never put this on a test. I would put something like find the derivative in terms of x with respect to x. You know, make it clear what it is that you're looking for. Right? So, you know, the in-class lesson is our opportunity to explore stuff. On the test, it's like I'm not trying to trick you. You know. All right. So for number 6, we're looking for a fact, something from the world of trigonometry, and just because I don't know what the backgrounds are, I'm gonna very briefly invent a relationship for you. So let me just get my my circle tool out. Okay, and I want it to be a line, and it should still be on. So another line. Okay, shape matched. Yay. And I'm gonna go purple for those who can score at home. And I'm gonna draw a little right triangle in there. I'm gonna try to have it matched up appropriately. All right. So this is a unit circle, or at least it's an attempt to be a unit circle. Every coordinate in space, and by the way, this is a little connection between parametric and polar coordinates, because polar coordinates is really just a more elaborate unit circle, right? So if you know your unit circle trigonometry, then that's not going to be challenging for you. Although I'm going to go over unit circle also, because you just don't know. Every coordinate in space can be represented as x comma y, or in 2 space anyway. 3 space, you throw in a z. But that would mean that if I decompose this, the 2 legs of my triangle are x and y. All right. Now, we do have some angle here called theta. This is a unit circle, a 1 unit circle, which means that the radius, no matter where you are on the circumference of the circle, the radius is always going to be equal to 1. All right. So one relationship that comes from this is that x squared plus y squared is equal to 1. But another relationship, actually 2 more relationships. One is that the sine of theta is equal to y over 1, or just y. And the cosine of theta is equal to adjacent over hypotenuse, x over 1. So therefore, x is equal to the cosine of theta. All right. So the consequence of this is that x and cosine of theta are the same thing on the unit circle, and y and the sine of theta are the same thing. So we get cosine theta squared, or cosine squared theta, plus sine squared theta is equal to 1. All right. That's a well-known fact. It's known as the Pythagorean Identity. You know this. You have used this. It's hit or miss as to whether or not you were given the origin story, right? So it might have just been like, hey, here's some rules, memorize them. Or maybe you got this. Maybe you got a better presentation. I don't know. But we have a relationship now, all right? And so that's all aside from what the question was asking, all right? So I'm looking at this rule, and I'll write now that it's a rule, and I look at what I was starting with in the problem. So this is the rule. The given is that x is equal to cosine theta and y is equal to sine of theta. So we're really going kind of right back in a circle here. Pun absolutely intended. So x is equal to cosine theta, y is equal to sine of theta. So if I do that direct substitution into my Pythagorean identity, I get x squared plus y squared equals 1. So it's kind of crazy, and that's why I like this problem so much. It's kind of crazy that in order to be able to convert this over from parametric to rectangular form, you need a rule. It turns out that that rule is what you need for this particular problem, right? You can't solve this particular problem without that rule, right? So I'm gonna chuck in another example here related to it, something that's not the unit circle. So I'll call it example 7. Do I have an example 7? I do? All right. So example 6a. 6b. That'll be 6a. All right, so let's say we have x equals, make it spicy here. X equals the cosine of 4 theta and y equals the sine of 4 theta. All right, so just to streamline it without all the extraneous explanations, it's same domain. The rule is that cosine squared theta plus sine squared theta is equal to 1. All right, so that just only accounts for an ordinary theta, but the extension is that cosine squared anything plus sine squared anything is also going to be equal to 1. So I can make the statement that cosine squared 4 theta plus sine squared 4 theta must also be equal to 1. And since we know that cosine of 4 theta is x, this would be x squared. This would be y squared, also equals 1. All right. Very strange. Good news. That's pretty much how trig works. You find an identity and then plug into it. But the strange aspect of this problem is that you're given 2 different parametric equations, yet you came up with the same rectangular equation. All right. Does anybody know what the coefficient in front of the variable of a trig function represents? There's a name for it. Period. Not the period. We use it to find the period. That's the right line of thinking, though. Frequency. Frequency. And the frequency tells us what? In simple terms. How often, yeah. So what we're looking at here is a frequency of 1 because the coefficient of theta was 1. Here's a frequency of 4, all right? So what that's telling me is you got this circle. The first set of parametrics only going to go around that circle once. This set of parametrics is going to go around it 4 times. Same path, but you're going to go around it more than once, all right? So whatever that coefficient is. Now, if you needed to compute the period, and while we're here, we might as well talk about that. So, sine, cosine graph. Generally in the form of y equals a I'll just go with sine. Bx plus c plus d. B is the frequency. 2 pi divided by b is equal to the period. All right. So that's telling you that when you're determining the period, it's telling you the length, the distance that you'd have to travel in order to complete one full cycle. All right. So, and while we're at it, I'll tell you the other stuff too. A is your amplitude, or the absolute value of A is the amplitude. Litude. Negative C over B is the phase shift. And D is the vertical shift. Yeah.
Remember doing this in high school?
High school, yep. Maybe pre-calc if you took that here. Yeah. I do it in college algebra. I mean, because what happens is as you get further up through the ranks, you end up spending less and less time doing stuff like this by hand. It's like, oh, I need the graph. I'll just look at the calculator, right? But this stuff is really important because we're going to get to some word problems, and those word problems are going to rely on your understanding of frequency. Now, also something to bear in mind, I just got through saying that the polar graph is just an expanded version of the unit circle. And the unit circle is based on our knowledge of sine and cosine functions, right? So when we start talking about polar graphs, I mean, we're going to be living in the world of trig, right? So a brief review is probably the way to go. And also, I'm not even talking about expanding it into 3D, because once we do that, then we're incorporating another component, so 3 angles if you're dealing with spherical to represent the location of a point in space, or 2 angles and a vertical distance if it's cylindrical coordinates. So, but both of them, in both cases, you need to know your unit circle trig. All right. So we hit that hard in this course. You kind of took a little bit of a break from it in Calc 2 in most cases, but then you come right back to it and you kind of dive in head first. All right. So all of these problems here kind of relate to the same idea. And I've just kind of addressed number 6 and 7 for you. So I'm going to skip those. I'll put stars on them and go right to number 8. You can cross off number 9 because they eliminated hyperbolic functions from the curriculum, so we don't have to worry about it. But the thing is, I leave it there because eventually they're going to turn around and put it back in, and I want to have my example ready to rock and roll. So, but for number 8, we have coefficients a and b in front of the trig function. So again, I know that cosine squared theta, but I'm going to use a, plus sine squared a is equal to 1. That I know. So what I'm going to do is I'm going to manipulate these so that they're solved for cosine and sine, respectively. All right, so in the case of the first equation, all I'm doing is dividing out an a. So cosine of t is equal to x over a. All right, and sine of t is equal to y over b. I think this is like the math lover's problem. If you like math, if you love math, then when you see the outcome for this, you can be like, wow, that's pretty cool. All right, so cosine squared, I'm just going to write parentheses squared, plus sine squared, same deal. I'm replacing the cosine, I'll go purple, with an x over a. And the sine is going to get replaced with a y over b. Now, I know I said before that you don't simplify unless you're told to, but this is one of those cases where I can't resist. So x squared over a squared plus y squared over b squared is equal to 1. Now, this is the moment of truth. Does anybody know what type of equation that is? Ellipse, exactamundo. So we just learned in parametric form the general model for the equation of an ellipse. That's pretty awesome. And, you know, if we knew about hyperbolic trig functions, you know, because they used to be in the Calc 2 curriculum, and so we build off of it in here, but it's gone. But this one would end up giving you the equation of a hyperbola, right? So same equation but with a minus sign, right? So if you remember conic sections from pre-calc, you probably remember them being kind of detailed. That's the nice way of putting it. A lot of tiny steps. You know, like you create the graph, but then you have to find all the coordinates, things like that. I would just ask you, if you had a choice, even just forgetting about the unit conic sections, you have a graphing calculator and the fighting spirit. Okay? If I tell you you have a choice, you can graph this equation in rectangular form or this set of equations in parametric form, what are you choosing? Every day of the week, twice on Sunday. Yeah, this one you have to solve for y in terms of x, and don't forget the plus or minus when you take the square root. So you're already not interested in doing that. Here, you're looking at two equations that are barely more complicated than a linear equation in terms of what you have to type into a calculator, right? But both of them are going to give you the equation, the graph of an ellipse. Also, just something to bear in mind. If you've ever tried in function mode, if you've ever tried graphing anything that's circular, you know, so anything that would fail the vertical line test, really, it doesn't do such a hot job of matching up the pieces. So, like, we would have to solve this for y in terms of x. We'd get the plus or minus. Then we have to put the equation in as two separate equations. And then the top half of the ellipse would merge theoretically with the bottom half of the ellipse, but it always leaves like a little gap. Like you just have to kind of believe that it's connected and it's fine, you get over it very quickly. But in polar form and parametric form, the calculator has no trouble whatsoever doing circular graphs.
Is that why the calculator didn't show the bottom half of exactly?
Correct. All right. So number 10, converting into parametric form. Right? We explored plenty getting it into rectangular form, but going into parametric form is a little bit different. So that being said, I think it's a lot easier. So it's not like we're building up in difficulty. So they tell us to let t equal x. All right, so now I know x is equal to t. Cool. So I can do my substitution because I'm just replacing x with t. Y equals t squared plus 2t. All right, so for my parametric equations, your calculator represents the notation somewhat different from the way that we do. Not crazy different, but I think it's different actually. Let me just look. Yeah, it uses subscripts. We're going to represent our parametrics using function notation. So we're going to say x of t and y of t. And despite what the calculator does, and this is the annoying part, using the parameter t as a lowercase t, right? Not the capital T, right? I think I explained why the calculator uses capitals more than lowercases because of the pixels, the rectangular pixels, so that's where it's at. All right, x of t is equal to t. And that was given right here. And then y of t would be equal to t squared plus 2t. All right. In the second case, if I cross multiply, I get x equals 2t. And then I can pop that in. Y equals meh squared plus 2 times meh. And again, just take note of whether a question asks you to simplify or not. Doesn't say and simplify, then there's no need to, but I'm going to do it. So 4t squared plus 4t. And so just to get it in the appropriate form, we're going to rewrite x of t is equal to 2t. Y of t is equal to 4t squared plus 4t. Now, a legitimate question would be something along the lines of, all right, cool, makes sense. What if you're not given the let statements? What if they don't tell you let t equal this, t equal that? The answer to that is, well, you can't do anything. If you haven't defined your parameter, you can't actually convert into parametric form. So you need to know what the relationship is between t and one of the two variables, right, in order to convert into parametric form. So in like a real life setting, parametrics are defined based off of data analysis, all right? So you would analyze the relationship maybe using a regression, linear regression or quadratic regression or something like that, the relationship between t and either x or y based on data collected over a period of time, and then that becomes your parametric substitution, all right? So what does that mean for us? It means I got to tell you what the let statement is, otherwise I'll have like, what do we got, 11 people in here now? 11 different versions of a solution to this problem on a test. So I'll have to say let t equal this, that, or the other thing, all right? So in the next one, x would be equal to t minus 1. So same deal. Oh, forgot my equal sign. Now for the other problems, when I was saying don't bother simplifying unless you're asked to, it was kind of like, yeah, well, there wasn't really much to simplify, so I'm just going to do it. Here, now, I really don't want to do it. I don't want to distribute this out. All right.
So in this, like, in example like this, we don't have to.
Correct.
Leave it like that.
Yeah, that's what I would do. So x of t, just to have the proper notation, t minus 1, y of t, t minus 1 squared plus 2 times t minus 1. And you know, like, I mean, I look at everything through a teacher lens. So I am looking at this and saying, well, instructionally, this is a better way of referencing the quadratic that comes out in your y equation, because that shows a translation, right? This would be a case where if you had an ordinary graph, t squared plus 2t, like if you knew what that graph looked like, that's great. This is just shifted 1 unit, every point shifted 1 unit to the right. So this is actually a more beneficial way of representing your equation than to actually distribute it out and get it into ax squared plus bx plus c form. Right? But that's just the way my brain works from like 20 plus years of experience. So if you don't think like that, that's not a knock on you. It's just I've been doing it longer, you know. So I better be thinking on a higher level.
You said initially x is equal to t minus 1. And then you go down again and say x of t is equal to t minus 1. What's the difference with it?
Oh, I was just rewriting it in the proper notation.
Oh.
Yeah, that's all.
So if you wanted us to simplify, would you say let t of x plus 1, and then next we write to simplify more, or how would you represent when you wanted us to simplify it?
And simplify.
Okay.
Yeah, it'll be very clear. I generally use italics on the simplified also, so it stands out. All right, so let's do some calculus. I mean, we touched on it a little bit, but let's do it, you know? So, you have two equations. It should be the next page of the new packet. Yeah, because the new packet is just a repeat of the old packet. Yeah, so this is... All right, so we're looking for the derivative dy dx, all right? But what this is telling me is that if I have an equation of x in terms of t and y in terms of t, I can take the derivative of those two equations separately and then just divide them, all right? Because mathematically, if you think about it, I'll show the work off on the side. dy dt divided by dx dt is the same, because these are rates of change, so they're fractions. It's the same as dy dt, keep change flip, times dt dx. The dt's would cancel, and you would be just left with dy dx. All right, so that's what I was getting at before when I was saying that there wouldn't really be much of a point in all of this if you couldn't take the derivative of your parametric equation without converting it over into rectangular form. And so what this is telling me is that there is a way. I just take the derivative of the two pieces separately and then divide one by the other. Now the second derivative is the weird one. All right, so I wrote the full derivation here, okay? So this is the part that you've got to understand. And it's so strange when you look at it, but it makes all the sense in the world, all right? So what I'm gonna do is, I think I'm just off on the side gonna rewrite it so that I can point out the important pieces. So we're looking for the second derivative of y with respect to x. All right, so what's going on is that we're taking the second derivative of the original function y. All right, so that's something that we have to bear in mind with respect to x. So that brings us to this part of the process. We're saying the derivative of the derivative. All right. Okay, so what that's telling me is that if I were looking for a derivative, dy dx, and then I were to tell you that the y, so where y, quote unquote y, is equal to dy dx, that's going to lead you to this statement here. All right. So that y is getting swapped out for a dy dx. So we have a d dx of this y, which is also a dy dx. So that's where this is coming from. All right, I couldn't think of a better way to do it than that. All right, so now I have to actually take the derivative, but I do know what dy dx is in general terms, I suppose. So I'm looking for d dx of dy dt over dx dt. The idea being that, yeah, the simplified form of the derivative equation is fine, it's wonderful. However, you're better off if you can get it in terms of t, because that goes back to the idea of, if I do it that way, I don't have to convert my original function into rectangular form before taking the derivative. All right. So now I just need to come up with a way to represent taking the derivative with respect to x of all of that. All right? And that actually brings us right back to go dy dx is the same as dy dt over dx dt. All right? So it's just I have a new y. So this is my new y. I'll put it in red. It's really saying dy dx. All right? So if I'm following that rule, it's dy dt over dx dt. All right, so then new y is my dy dt dx dt. All right. And that's really in a nutshell the rule. It's just you could go the next step and say, well, it's dy dx, but I don't want to do that, right? Because I want it to be in terms of t. So that's a glorious mess. However, if you really think about it, we got everything we need. All right. So the formula is wonderful, but it could also cause problems. So what I'm going to do is I'm going to put it in words. We're going to create a process out of this. So we're going to take the derivative. And that's dy dx equals dy dt over dx dt. Then you're going to take the derivative again. Take derivative of dy dt over dx dt with respect to t. Then finally, we're going to divide by dx dt. I'll make them like little bullet points here. Boop. Boop. And boop. Some people are perfectly fine with rules. I give you a rule, you memorize it, you apply it, no problem. No muss, no fuss. Personally, I like looking at the rule and deciding what it truly means. So I'll take you through an example, and then we'll come back and talk about the arc length stuff. All right. All right. So these are the rules, the formulas for arc length. They're wonderful, but that's not what we're here for. We're here to see where those formulas came from. Okay. So let's take a look at this. It took me a little while to actually make these diagrams, but I'm pretty proud of what I did. Wait a minute, I'm thinking of something else. There are diagrams in this packet somewhere that I'm really proud of because it took me a while to make them. These I just snipped out of the textbook. So, all right, so what we're doing over a closed interval a to b is we're measuring minute little distances along the curve. Right? I always equate it to the idea that if you were to measure a distance around a circle, for example, right, you want to find what the circumference is of that circle. There's a couple of ways you could do it. One way would be to actually use the circumference formula. Another way to do it would be to start off at the beginning and then just measure out little teensy tiny little segments, right? Whatever parts of it you deem to be as linear as you can. Like I wouldn't measure from here to here necessarily because I lose some of the curve, but I can do maybe from here to here. That little chunk, get that distance is like 1.5 inches, almost 2 inches, and then pick up over here, get the next linear piece, another inch, then do it again and work my way around. It's not going to be exact, it'll be an estimate, but you know, maybe it'll be a good estimate. If it's a circle with a very large radius, it's not going to be as curvy because of the, you know, like we're standing on a circle that's a very large radius. And if you get the cross section, you know, you just slice it right down the middle and get like a slice of the earth, you'd be looking at something that's circular, okay? But it doesn't, I don't perceive that I'm walking on something that's curved, okay? So the larger the circle, the less curvy it is, okay? And later on in the course, we're gonna learn how to compute the curviness of a function, right? So that's pretty cool, it's called curvature. But if you have a circle with a very small radius, that's very curvy, okay? Same idea with functions. If you have something that is like parabolic or like a crazy polynomial function, it's going to be curvier than something that's a little bit more linear, right? But what we're going to do is take little tiny little segments of that curve and figure out what their lengths are. And we do that using the Pythagorean theorem, right? But the idea is that we're not actually going to get a tangible distance. Like these distances here, even though it looks like it's something I could measure with a ruler, this is so infinitesimal that I could never measure it. It's like the idea of the infinitely many-sided polygon. So if I start off with a triangle, then we get a square, increase the number of sides, then it becomes pentagon, hexagon, septagon or heptagon, then octagon, nonagon, and so on, and we continue on and on and on and on and on, it becomes more and more circular. If you could squeeze infinitely many sides in there, it would be a circle, all right? Those sides would have infinitesimal length, all right? The length of any one of those sides would be dc, all right? Delta, lowercase delta, which we abbreviate with a d, and c for circumference, all right? A minuscule smidge of circumference, all right? That's all I'm looking at here. But if I want to represent it tangibly, I have to actually give it some distance, all right? So one side is the horizontal change, one side is the vertical change. Pythagorean theorem tells me that the hypotenuse is going to be the square root of the sum of the squares, all right? So then it just becomes a matter of, okay, that's wonderful. Now what do I do with that, all right? So let's investigate. So I know that some minuscule arc length, which is abbreviated with an S, all right? Do I state that anywhere? Kind of, but I'm going to make it more obvious. Arc length. All right, ds is the smidge of arc. All right, it's not over an interval. It's just it's what we would call, if it were such a thing, an instantaneous distance. All right. We know that that's going to be equal to the square root of dx squared plus dy squared. All right. Now, these are parametric, so there's a time component. So what I'm going to do, sorry, I'm a frog. Ugh. I'm going to divide both sides by by dt. to manufacture a ds dt. All right, because if I want to, because eventually I want to be able to get just ds, not ds, so I'm going to have to integrate. And so when I do that, you know, like we don't just integrate typically a dy without a dx, right? So I'm just introducing it. I'll introduce it on one side. If I divide one side by dt, I got to divide the other side by dt. I want to see if I can consolidate things though. If I could get this under that radical, that would be great. So that's what I'm going to do. I'm going to put it under the radical. All right. But I can't just plop a square root over it. I need to come up with an equivalent expression. So what I'm going to do is square it and then take the square root. All right. I'm going to do opposite operations because that'll give me an equivalent expression. So I have a dt still. I introduce the dt, I square it, and then I take the square root. So if I put the number 2 in there and square it, it becomes 4. Take the square root, it goes back to 2. All right, so the square root of 2 squared and 2 would be the same thing. So the same idea just with the 2. All right, that's going to allow me, sorry, to put it all under the radical. It's the result of two fractions being added together, essentially, so I'm just going to undo that. So dx squared over dt squared plus dy squared over dt squared, all under the radical. Which I can represent further as just dx dt squared plus dy dt, also squared, and that's equal to ds dt. All right, so looking pretty good. I can get ds alone now. I just multiply both sides by dt. So ds would be equal to all that stuff again. Multiplied by dt. My goal being that, again, I want to get an s. All right. There's an understood 1 in front of the ds. I'm just going to put it there. So I know what I'm integrating in the next step. All right, because I'm going to take the antiderivative of both sides. Antiderivative of 1 with respect to x would be x, but it's s here, so it's going to be s. And so that's our general or most general rule. But the thing is, arc lengths are finite. They don't exist over an infinite interval. So we'll have to bound it.
Are we not using one down the test?
Yeah, I always put one proof on the test. So it could be this, it could be the one above, where I ask you to justify the second derivative process. But I always ask you to prove something. Okay. What was the other one? Oh, the unit circle rule in parametric form that we did earlier. That's a possibility. I'm pretty transparent though, so when we're reviewing for the test, I'll tell you what to be on guard for in terms of the proof. But every test will have a proof on it. Right, so yeah, because it's not infinite, we don't want to just leave it like this. We don't want it to be boundless. So we would go over the interval of a to b. All right. And so that's the origin story behind the arc length formula in parametric form, which I think is actually easier than the one in function form question.
It's pretty stupid, but should we get rid of the radical and the square, which is each other?
The plus sign screws that up. Yeah. If that wasn't there, then you could. So, if you look at the structure of it, I mean, if I ask you to use this, it's not a problem, because all you're doing is basically the same stuff you would do if you were finding the derivative. It's just you're putting it in this form rather than the other form, right? So let's see an example, and then we'll see where we're at after that, right? But you know, like most people, like at first they're like, oh man, I gotta do that proof on the test, that sucks. And then you realize that it's really just it's a script. You know, like if you get the concept, then maybe it's not, because then you can actually invent the rules, which is kind of cool. That's kind of what I'm going for. But worst case scenario, you're just memorizing steps. And then on top of that, I allow you an index card for the first test. So what I found people doing is they don't really put much on their index cards. But what they do end up putting are steps on the calculator, like how to use the calculator, and a proof or two. You know, whatever, you know, because, you know, to put them all down is kind of unreasonable. But you put down one or two, you know, the ones that you would probably have trouble remembering, and then it ends up working itself out. And I also give you an omit on every test. So there's the format of every test is 10 questions. You can omit one, and you get the points for the question that you omit. So once you decide to drop a question, I automatically give you the 5 points for that. Then you got the proof.
Is that every test?
Every test, yeah. So then you also have a proof. So out of the 10 questions, one can go away. The other one you kind of know going in advance, so you're already ahead of the game. You know, so like you got some of the credit before you start the test, really. All right, so I'll talk more about. So given parametric equations, find dy dx, so first and second derivative. All right, so what I'm going to do first is just off on the side, I'm going to jot down the x equation in its most convenient form. And I'm also going to do the same thing for the y equation. But the y equation is already in its convenient form. Most convenient is power rule ready. All right, so if it's in the form that's ready to apply the power rule, then you're in good shape. I know some folks like to go with the prime notation for derivatives. I would caution against that, because we're going to be taking derivatives with respect to a variety of different variables. It's very easy to lose track of what you're differentiating with respect to. So the dx, dt, dy, dt, that notation is a better way to go. All right. So the first derivative of 2t to the 1/2 would be what? T to the negative 1/2. All right, and what about 3t squared minus 2t? 6t minus 2. Exactly. So I just need dy dx, which is dy dt over dx dt. So 6t minus 2 over t to the negative 1/2. Now, it's up to you at this point if you want to leave it in this form, but I say the same thing in my Calc 1 and 2 classes, where I tell them you don't have to simplify unless I tell you. But in some cases, it's in your best interest to simplify even if I don't tell you. You got to take the second derivative. You want to take the second derivative of this, or do you want to take the second derivative of something that's simpler? I think we all know the answer to that. All right, so I'm going to clean it up a little bit. So the negative power can bring that t up to the top. So t to the 1/2 times 6t minus 2. And then I'm just going to run it through. Distribute it. 6, that's not a 6. Crazy. 6t to the 3/2. Keep the base, add the exponents. Minus 2t to the 1/2 power. Power rule ready. It's the name of the game. So my second derivative, I want to take the derivative of what I just got. So notation-wise, d dt of dy dt over dx dt. Get that whole answer and divide it by dx dt. So the derivative with respect to t, I'm going a little heavy with the notation. You wouldn't necessarily write all this. You can skip around stepwise. I'm just doing it for note-taking purposes. So 6t to the 3/2 minus 2t to the 1/2. That's what I'll be differentiating. But on the bottom, dx dt, I already know that. All right, that's t to the negative 1/2 power. All right, so whereas before with the first derivative, it was in my best interest to simplify. Once I get the derivative of the top, I don't need to simplify, all right? Because there's no value in doing that, all right? So power rule. What's 6t to the 3/2 going to become? What do we say? 9t to the 1/2, yeah. Then minus, the bottom's going to stay put. Negative 2t to the 1/2 becomes to the negative 1/2. Clean that up a little bit. And like I said, it's up to you if you want to go further with it. It actually kind of cleans up pretty nicely if you go further. Because it would be the same as saying t to the 1/2 times 9t to the 1/2 minus t to the negative 1/2, and then run it through. Keep the base, add the exponents, you get 9t minus 1. So a lot nicer than you would probably expect. And that tends to happen. You know, you got some problems that look like maybe a monstrous mess, but they end up becoming all right in the end. All right, you got to see it through. All right. So that's the skill associated with it. So it's not terrible. Just takes a little time. I'm going to put a star on numbers 2 and 3 because these are the kind of problems that I want you to experience before I go over them. I don't want to just take you through them right now because if I did, then I'd be removing all the thinking on your end, and so that's not a good thing, right? So like, I want you to experience these problems. Succeed, fail, it doesn't matter, we'll go over them together, all right? But try them first before I go over them. So let's go back a page and talk about arc length. But I can tell you that my tests are not designed to be feared. All right, they're designed for you to show yourself, not to be terrified of the experience. All right, so, but you'll see as we get closer. So hopping up to page 7, we'll tackle number 4 together. And then I'll just preemptively put a star on number 5. kind of reserving my teacherly right of doing the easier one with you and then leaving the more challenging one for you to try on your own. All right. But it's the same rules as the other starred problems. It's you're going to try it, succeed or fail, and then we'll go over it together anyway. All right. So just bear that in mind. So we're finding the arc length on the interval of 0 to 1. All right. Sometimes helpful to create the graph to get a sense of what you're up against. But when I say create the graph, I mean pop it in your calculator, take a look at the picture. All right. So I'm not talking about a scaled drawing. Regardless of what you do first, ultimately you're going to have to figure out dy dt. It doesn't matter which one you do first, but when I do the derivative process and second derivative, I usually find dy dt, then dx dt, so that I divide them in the proper order, but this isn't that. All right, so dx dt is 2t. dy dt is equal to 12t squared. All right. Now our rule is that the arc length is over the interval of a to b, dx dt squared plus dy dt squared dt. So over the interval of 0 to 1, all right, they gave us the restricted bounds. You got to be careful with circular functions, anything that's a closed loop, because sometimes they don't give you the domain, but you have to know, well, it's a circle, so it's got to be between 0 and 2 pi or 0 and pi, depending on the frequency. All right, so just something to be cautious about. dx dt is 2t, so 2t squared, quantity squared, plus 12t squared squared. dt. On the interval of 0 to 1, we're looking at the square root of 4t squared plus 144 t to the fourth dt. All right, now there's some common factors that can be pulled out. And then you can go that route. In this case, you'd be doing a little trig substitution in order to find the integral. The scheduling process happens so late in the summer, so I normally I can point to like and make comments like, well, you all took me as a teacher for a reason, so here's the reason, you know, but I don't know that that's necessarily the case. So this could be a surprise to many of you. My policy on definite integrals, because I don't like to do a double dip, you've already been assessed on this in Calc 2. My policy on definite integrals is pop it in your calculator and get the answer. All right, it's indefinite integrals where you have to do something else potentially. All right, so and you know you'll get enough situations where you have to do stuff by hand, you won't have a choice, that I don't worry about like, oh, you didn't do it by hand, that means you don't know math or something. I don't know. Different people have different philosophies, but I find that most of the people who take me as their teacher for this course are doing it because I allow a more liberal use of the calculator, right? So if you didn't know that coming in, surprise. If you did know it coming in, then I just confirmed what you already knew. All right, so bottom line is I'm going to kick over to the computer. I'm going to remind you how to find a definite integral on the computer, assuming that it actually wants to function. Oh, that's computer 2. 1, I mean, so it's probably computer 2. Right. This is just go. Just one of those. We do what we can. Math 9. You can scroll down, but it's the one that says FN int on your calculator. It won't look like that on the screen, assuming that your screen is set up properly. All right, it should look like just a good-looking blank integral. And then in that blank integral, you just type. All right, so that's what I'm going to do. 0, hit the up arrow, 1, right arrow, square root. You could use x's, t's, whatever. I'm going to use x's. 4x squared plus 144 x raised to the 4th. Pop an x on the outside. And then hit enter. And you're looking at about 4.149. So approximately 4.149. Say it again?
I did put it in.
You did it a different way?
Yeah, I put it in to graph, and I put
Y1?
then I put second trace, and then I find the end where it's like 0 to 1.
Oh. And you got the same answer?
Yeah, let me show you.
Oh, because you did second trace, option 6.
Option 7.
Oh, 7, yeah, because 6 is derivative, yeah. Yeah, that works.
Where'd you put that again?
Math, option 9.
Okay. Thank you.
No problem. Oh, this doesn't lock in place. That's unfortunate. All right, but let me just show you really quickly. A shortcut key, alpha window. The newer calculators have more stuff, but the older calculators have the first 5 options. This is like the most commonly used, but not the easiest to find set of functions. So odds are, if you're looking for some weird function in your calculator, it's in this menu, and that's alpha window that brings that up. All right, so in that case, you just choose option 4 and you're good to go. All right, so it's a little quicker and easier that way. So kill that, kill that. You'd be looking at the square root. It would become 2t, and then 1 plus 36 t squared.
Okay.
dt, and then you'd let u be equal to 1 plus 36 t squared. And then you'd be looking at, when you take the derivative of this, du is equal to 72 t dt, with the idea being that we want to get rid of these guys. So I have 72 t dt. I want a 2 dt, 2t dt. So I'm going to divide both sides by 36. So 1 over 36 du would be equal to 2t dt.
Okay.
So then that would allow this substitution to happen. So I'm going to replace the 2t dt with that. So it's going to become 1 over 36. The square root, instead of 1 plus 36t squared, that's going to get replaced with a u. And then we'll have a du going from 0 to 1. Well, actually, it wouldn't be 0 to 1 anymore, so we'll just leave it without bounds. So then it becomes 1 over 36 u to the 1/2 du. Increase the exponent by 1 becomes 3/2. Divide by the new exponent, so it's the same as multiplying this by 2/3. So we're talking 1 over 54, if I'm not mistaken. Oh wait, we're multiplying it by 2/3. So 1 over 18, just make sure. Yeah, 1 over 54. right? And so that's the same as 1 over 54 times 1 plus 36 t squared to the 3/2, and then you would evaluate that over 0 to 1.
Okay, that's going, this is going.
Right. So if I put the 1, let's see, the 1 makes it clean. Yeah, so 1 over 54 times, I'll just write it, yeah, 2 to the 3/2 minus 1 over 54 times 1 to the 3/2, so just that. Yeah, I don't think it would clean up any more than that without the decimal point.
Am I registered now?
What's your last name again?
Menezes?
Yes.
Oh.
You're definitely in there.
Thank you very much.
No problem.